I'm Dr. Roger, and today we're looking at differential equations, in particular the Laplace transform of the trig function f of t equals cosine of at. We write the Laplace transform as an uppercase cursive L, set brackets, and then our function, or as the uppercase letter corresponding with our function. So instead of lowercase f of t, uppercase f, now with the variable s. And the Laplace transform is an integral transform. Integral transforms the integral from alpha to beta of some kernel k of st times our function. In this case, alpha and beta are 0 and infinity. Our kernel k of st is e to the negative st. If we were working with, for example, the Fourier transform, that's a different kernel, and wavelet transforms have a variety of kernels that are also different. But the Laplace transform turns out to be particularly useful for differential equations, as we will see later. So I'm going to find that improper integral, and that will be parts, of course. I'll write my scratch work down here. U equals the exponential, so du is negative s e to the negative st. I could use the trig function as u also. It doesn't matter with exponential times sine or cosine. dv then has to be the cosine at dt. So v is 1 over a times the sine of at. Derivative of positive sine is positive cosine. Chain rule cancels 1 over a, so I did that correctly. So this integral is uv 1 over a e to the negative st sine at minus the integral of v du minus the negatives plus s over a e to the negative st sine at dt, and all that stuff on the right is from 0 to infinity. I need 0 to infinity for this function that's not an integral, so I'm just putting it outside rather than in my limits of integration. And I get to do parts again for this integral. So my original integral is 1 over a e to the negative st sine at, and then plus whatever I get from parts. So parts, I'm going to have u equals the exponential again, e to the negative st. So du is negative s e to the negative st. And dv equals the trig function. I'm going to keep the coefficient with it, s over a sine at. And I put the coefficient inside my integral because I'm less likely to forget to distribute it if I do that. So v is negative s over a squared cosine at. Derivative of negative cosine is positive sine. Chain rule gives me an a that cancels one of the a's from a squared to just give me a denominator of a, so that's correct. So this is uv minus s over a squared e to the negative st cosine at, and then minus the integral of v du. Minus 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 is minus the integral s squared over a squared times the integral 0 to infinity. I'm going to put in my limits here now for the non-integral terms of e to the negative st cosine at, and I have my s squared over a squared. The negatives cancel, but there's another negative from the formula. And this is my original integral. So if I add s squared over a squared times my original integral to both sides, I have 1 times my original integral, and I can write that as a squared over a squared times that integral, so that when I add to both sides, common denominator. So that is s squared plus a squared over a squared times the original integral. Equals, I'm going to write this formally as the limit as b goes to infinity of 1 over a e to the negative st sine at minus s over a squared e to the negative st cosine at from 0 to b. And on the right, for s greater than a, as b goes to infinity, e to the negative sb goes to 0, sine of 0, sine of ab is bounded between negative 1 and 1, so the first term here goes to 0. Similarly, this exponential also goes to 0, and we only have to worry about what happens at t equals 0. E to the 0 is 1, sine of 0 is 0, so minus 0, and then minus negative is plus s over a squared, e to the 0 is 1, cosine 0 is 1. On the left, if I multiply by a squared over s squared plus a squared, and do the same on the right, all I have left is this integral, which is the Laplace transform of cosine at. This is the definition of the Laplace transform. And on the right, a squared over a squared is 1, so I'm left with s over s squared plus a squared for s greater than a. And that gives us the transform of cosine at. It's important to know where all these Laplace transforms come from. It's okay to just use them from the table once you understand the transform process, but the origin of this transform is important so that you understand the math. Come back soon for my next come back soon for my next differential equations video. With math, there's always more.